In the serene silence of space, a hidden crisis looms, one that threatens the very fabric of our technological advancements. This crisis is known as space debris or orbital pollution, a byproduct of humanity's exploration of the cosmos. As we gaze up at the stars with wonder, we must also confront the challenge posed by the remnants of our activities in orbit. How did we reach this point, and what can we do to safeguard our future in space? The journey of a satellite begins with the thrill of launch, where it ascends into the great unknown, fulfilling critical roles in communication, navigation, weather forecasting, and scientific research. From small CubeSats to massive communication arrays, each has a unique purpose and contributes to our daily lives in ways we often take for granted. However, once these satellites complete their missions, they often become space debris, defunct objects that can no longer serve their intended purpose. This end-of-life phase is a critical juncture, marking the transition from a valuable asset to a potential hazard. Space debris encompasses a wide range of objects, from defunct satellites and spent rocket stages to small fragments resulting from collisions or explosions. Currently, there are over 36,000 pieces of debris larger than 10 centimeters orbiting Earth, with millions of smaller fragments scattered throughout low Earth orbit. These objects travel at staggering speeds, up to 17,500 miles per hour, making even the tiniest piece a significant threat to operational spacecraft. The increasing density of debris in certain orbital regions creates a chaotic environment, raising the stakes for satellite operators and astronauts alike. The origins of space debris can be traced back to the dawn of space exploration. The first significant contributor was the 1957 launch of Sputnik 1, the world's first artificial satellite. As nations raced to explore space during the Cold War, numerous satellites were launched, and with them came the inevitable generation of debris. Events like the 1986 destruction of the Soviet Union's Cosmos 954 satellite, which re-entered the atmosphere and scattered radioactive debris over Canada, and the 2009 collision between Iridium-33 and a defunct Russian satellite exemplify the escalating risks posed by space debris. The latter incident alone generated over 2,000 trackable fragments, amplifying the debris problem and highlighting the fragility of our orbital environment. The exponential growth in satellite launches since the 1990s has significantly contributed to the current state of orbital congestion. From a handful of satellites in the early days to thousands today, with the rise of commercial satellite operators deploying large constellations like SpaceX's Starlink, the number of objects in low Earth orbit is projected to continue increasing. This surge poses an urgent challenge. How do we manage and mitigate the risks associated with such a congested orbital environment? To address this challenge, scientists and engineers have developed sophisticated tracking systems to monitor space debris. Ground-based radar and telescopes continuously scan the skies, cataloging thousands of debris objects and predicting potential collisions. Organizations like the U.S. Space Surveillance Network, SSN, play a pivotal role in tracking debris, providing vital information to satellite operators to help them avoid potential impacts. In recent years, advancements in technology, including the use of machine learning algorithms to predict debris movement, have enhanced our ability to detect even smaller debris objects, increasing the effectiveness of collision avoidance strategies. The risks posed by space debris are not just theoretical. Each year, active satellites must perform numerous collision avoidance maneuvers to steer clear of potential impacts. This not only increases operational costs, but also affects the reliability of critical services, from telecommunications to GPS navigation. The potential for a Kessler syndrome scenario, where a single collision generates more debris, leading to a cascading effect, is a reality we must take seriously. As the density of debris increases, the likelihood of collisions grows, creating a perilous environment for future space missions. This could severely limit our ability to explore space and utilize its resources. The quest to mitigate space debris involves innovative engineering solutions and international collaboration. Various active removal technologies are under development, such as robotic arms, nets, and harpoons designed to capture and deorbit defunct satellites. For instance, the European Space Agency's Remove Debris mission aims to demonstrate these technologies in orbit. Additionally, innovative satellite designs that include deorbiting mechanisms, such as drag sails and propulsion systems, are being integrated into new satellite launches. These mechanisms allow satellites to lower their orbits at the end of their operational life, ensuring they re-enter the atmosphere and burn up, thus reducing the risk of contributing to space debris. Collaboration among spacefaring nations and private companies is essential in addressing the challenges of space debris. Initiatives like the Space Data Association, SDA, promote information sharing among satellite operators, fostering a culture of safety and awareness in orbital operations. Furthermore, international frameworks such as the United Nations Office for Outer Space Affairs, UNUSA, guidelines urge nations to adopt best practices for satellite design, operation, and end-of-life disposal. It's crucial that these guidelines evolve to address the unique challenges posed by megaconstellations and other emerging technologies. The societal implications of space debris extend beyond technical challenges. They touch on public awareness and education. As the world becomes increasingly reliant on satellite technology, it's essential for the public to understand the stakes involved. Educational initiatives aimed at schools and communities can raise awareness about the importance of responsible space exploration. Young advocates, inspired by the beauty of the cosmos, can champion sustainable practices, urging both governments and private enterprises to prioritize debris mitigation efforts. The economic implications of space debris are profound. Insurance costs for satellites have risen as the risks associated with orbital collisions increase. A single collision can result in losses that run into hundreds of millions of dollars, impacting not just the operators but also the global economy. The rising costs associated with insurance, potential losses, and collision avoidance maneuvers underscore the urgent need for effective solutions. However, the challenges also present opportunities for innovation. Companies specializing in debris removal and satellite servicing could emerge as vital players in a new space economy. As we stand at the threshold of a new era in space exploration, the lessons learned from our past can guide us toward a sustainable future. Innovations in satellite technology, such as end-of-life disposal systems and designs that minimize debris production, pave the way for responsible space activities. By adopting a stewardship mentality, we can ensure that space remains a realm of discovery and inspiration. The challenges posed by space debris serve as a reminder of our responsibilities as stewards of the cosmos. As we continue to reach for the stars, we must do so with an awareness of our impact on the environment beyond our planet. By embracing sustainable practices and fostering international cooperation, we can preserve the wonders of space for future generations. What legacy will we leave behind in the universe? And how will we ensure that our exploration continues without compromise?